To welcome everybody to the third talk in our colloquium mini-series on thermalization and equilibration dynamics in quantum and classical many-body systems, hosted virtually at Washington University in St. Louis. And so it's already halftime, and I'm extremely happy to announce another great speaker for this occasion, which is Gil Refael. And this is a special pleasure for me, as I have known Gil for a long time. Actually, since right after he graduated from Tel Aviv with a bachelor's and a master's. That is, since his days as a graduate student at Harvard, which started in 1998. So at Harvard, he worked with Daniel Fisher. We met on a different campus, though, I think, a little further to the southeast, where Gil certainly also had a presence early on. So we met during our lives as graduate students, and Gil graduated in 2003 and became a postdoctoral fellow at KITP and joined the faculty at Caltech 2 years later in 2005, where he very quickly moved through the ranks and is now the Taylor Lawrence Professor of Theoretical Physics. Gil is widely known for his many contributions to condensed matter. He's an expert on disordered systems, the role of topology, as well as dynamics and quantum control. He's widely recognized for his work on Majorana fermions, Floquet topological insulators, topological-polaritons, and many things more. His work has earned him numerous prestigious awards and recognitions, such as the Sloan Fellowship, the Packard Fellowship, the Cottrell Prize, the Bessel Prize, and the Simons Investigatorship. So he is, among other things, the perfect person to put a topological spin on our mini-series. So please all join me in welcoming Gil Refael. Gil, thanks so much for being with us today and telling us about topological physics at the light-matter interface.
Yeah, thanks so much, Alex, for inviting me, and thanks, Alex and Alyosha, for organizing this and inviting me. It's a pleasure to be here. I see a lot of familiar faces, so hi, everybody. I see some familiar faces that might have heard this talk before, so apologies to you. And let's see, so my talk today is kind of a review of my adventures in over the last decade in thinking about topological ideas implemented at the light-matter interface. So I will give a rather lengthy review of what I see as topological quantum physics, or the basics of topological quantum physics, and then work my way through this decade of my research life, talking about Floquet topological insulators, the topological polaritons that Alex mentioned, and ending, I think, with my current research on energy pumping in driven vial semi-metal. So two things. One, Alex, thanks again for the lovely introduction, and it's been a pleasure to also get reminded of like grad school years back in Boston. And second, I wanted to say, please interrupt me with questions whenever you want. I would not mind that at all. So I guess, Alex, you're probably moderating. So if you see raised hands, just stop me. It would be great to have questions in between. And, you know, if I don't make it to current research, no worries. So thanks for joining. So we can start. So the first, let's see. Okay, so the first thing I wanted to discuss before talking about topological applications and the dynamics of quantum systems, what is topological? So we all know that topology has to do with invariance of shapes, some features of shapes that do not change with continuous manipulations. Number of holes, for instance, is the order of genus. And we can think about it from the perspective that we can take an example of a sheet of paper. We can wrap it up to make a cylinder. And now we're faced with two options, right? We can take, can you see my cursor, by the way?
Yes, we can see it. Mm-hmm.
Excellent, thank you. We can take the two sides of the cylinder and bring them to a point like we would do with the wrapping of a lollipop. And that will give us a sphere, essentially. Or we can do another thing. We can take one side of the cylinder and connect it to the other side of the cylinder to give us a torus. And in fact, every time that I think physicists talk about topology, they give this example of a torus that's the same as a coffee mug from a topological perspective. And that's just because we're obsessed with coffee and bagels. Some of us are obsessed with donuts, so we give a different picture. But why is topology appearing in physics? I think, to me, the most visceral example of topology in physics comes in vortex physics. For instance, in weather, this plays a very significant role. I mean, you can see immediately the difference between a breezy, clear day and a hurricane, where the hurricane has a vortex in the velocity field with the topological defect at the center, where the velocity has to vanish. And if you want to get rid of a hurricane, well, you can, of course, you can try to nuke it. Experiment to be done still. Or you can try to remove the center of the vortex out of the pattern to make this pattern into a linear breeze that can then decay. Of course, we cannot do that because this is like many tens of miles feature. And the only thing that can kill a hurricane is landfall, where the land just suppresses all velocity at the same time. So this is a highly stable weather pattern, unfortunately. And the same thing happens for electrons. Say in superconductors penetrated by magnetic field flux lines, the electrons form kind of like hurricanes around the flux lines. And the only way to get rid of these flow patterns for the electrons is to get rid of the vortex line, to get rid of the flux line, take them out of the superconductor. So I think for many years we were obsessed with this manifestation of topological aspects in physics, of topology in physics, where these vortices created these stable excitations in superconductors that determined the electromagnetic response of them. And I certainly spent a long time in my PhD thinking about these objects. I have to say, I am reminded that topology plays a role even in other professions. And I wanted to make sure that in this colloquium it comes out clearly. For instance, archaeologists must care about topology. Like you can take a look at this jug from the ancient Roman Empire era. It has genus 1. And you can compare it to this jug, which has genus 2 from the same era. I know that topology matters because the left jug costs $12,000. The right jug is genus 2. There isn't even a price mentioned, so it must be priceless. That must be dependent on the genus. There's no other explanation. I think wine enthusiasts also care deeply about topology, and I inferred that from looking at various carafes. Here's a genus 0 carafe. Here's a genus 2 carafe, right? You have one hole here and one hole here. And you can even have a cool design with genus 1. I don't know what the prices of these things are. You know, I never do internet shopping, you have to know this. Of course, there's also body art topology, but I don't like dwelling on it too much. So going from that back to physics, what is topological in physics? So I talked about vortices, but you know, we're in a new era of topological quantum physics. There, we can still have the same ideas, but we have to implement them in momentum space. It's going to be the theme in the next couple of slides. So what is topological in quantum physics? The most important thing for us is spin physics. Spin half, familiar particle, we all know to love it. It's described by a spinner that has 2 dimensions, two entries, which are given by complex numbers dictated by the direction that the spin takes on the Bloch sphere, theta and phi in the xy. We all know how to do this. But the point is that in the same way that the velocity field was winding in a hurricane, the spin direction can wind in quantum systems. It can be in real space to give us things like fermions, but it can be in momentum space to give us things like topological insulators. So how do we get the spin to wind? The first component is a spin-orbit coupling. So if you imagine electrons in the wire, they have a p-squared dispersion that I'm not writing, but they might have a spin-orbit coupling term, which is the spin in the z direction dotted with the momentum along the wire. So right-moving electrons may want to point up. Left-moving electrons, based on this, would like to point down in their ground state. So this is like a momentum-dependent magnetic field, which is really neat. It's been there forever and ever, right? Many decades we've been talking about spin-orbit coupling. That's what it is, a momentum-dependent magnetic field. Oops. Now, there is no such thing as a continuous quantum wire, right? Everything is broken apart to atoms. And instead of thinking about a continuous quantum wire, let's think about a array of atoms, a tight binding model for an electron. An electron can hop, say, between nearest neighbors. It can have a wavelength, can have a debris wavelength, which is twice the lattice constant. That's the maximum wavelength it can have. And you know, it has a band structure, and instead of p-squared dispersion, we're going to have a periodic band, which goes like cosine of the momentum, roughly like this. And I'm suppressing h bar over a, is the quanta of momentum in this case. We're just thinking about momentum as an angle. And we know the band structure is a periodic in momentum. So momentum can go from minus pi to pi times h bar over a. Now, if momentum is periodic, it gives us a circle. And we can now ask what the spin does on that circle. So if we now generalize a spin-orbit coupled wire into a spin-orbit coupled tight binding model, let's just write down Hamiltonian. It's a time-honored tradition in this field to just write down Hamiltonian. So here's my Hamiltonian. Instead of cosine p, just bare dispersion, let's think about spin-orbit coupled wire, which has spin in the x direction times cosine p, minus spin in the y direction times sine p. Now, if you choose momentum, it is as if you have a magnetic field that winds as a function of momentum in the xy plane and gives you, in this band structure, the lowest band would have a spin that changes as a function of momentum on the xy plane. We should, and this gives you something like a vortex for spin in this momentum ring. You know, the momentum is periodic, going from zero momentum plus minus pi. And in this band, we'll have a spin that winds accordingly, with the momentum kind of being like the angle of the magnetic field. Now, we should get used to semi-classical dynamical considerations. So for instance, if you have an electron that's sitting in the bottom of a band with the spin pointing in the right direction, and of course moving slowly to the right with the spin in the x direction, when we probe this band structure in other places, we can get electrons moving faster because that's a group velocity with a different spin component, and so on and so forth. Spins moving slowly to the right near the end of the band. And likewise, looking at negative momentum, we see that the spin is pointing in the negative y direction with a motion that depends on the derivative of the energy with respect to momentum. I know we all know this, but I wanted us to get used to the idea that we have a motion that's coupled for the spin and location, and that we need to consider these two things together. The spin direction is a function of momentum, and the dispersion is a function. Now from this, we can make a one-dimensional topological phase. In fact, this one-dimensional topological phase, I think, was first proposed by Alexei Kitaev, describing a superconducting spin-orbit coupled model. Well, actually, I should say that what Alexei wrote was a p-wave superconductor model that will have that has essentially the spin-orbit coupling that I showed before, but instead of spin, he had Nambu coordinates of particle and hole superconductor. But the same Hamiltonian gives rise to two edge Majorana states And that started off this idea of topologically protected quantum computing with Majorana fermions. This was the model that he suggested. Now, this talk is not about Majoranas. This is such great work. So I'll just mention this. That these Majorana fermions give topologically protected quantum memory because each Majorana fermion on its own doesn't have any measurable properties, but when you bring them together, they give you a single fermionic state that can be either full or empty, either odd parity or even parity. And that could be used as protected memory because when the Majoranas are apart, you have no idea what that state is. Now, so we talked a little bit about 1D topological phase. And I think for my talk, I want to also cover 2D topological phase in the most simplest manner. So let me ask quickly, are there any questions anybody wants to raise?
At the moment, I see no questions.
Is this, do you want me to speed up to the introduction, or is this something that's...
I think this is perfectly fine.
Let me know. It's like, think of me as a video player, fast forward, rewind, no worries. I guess in YouTube, you can actually do it in the end. I cannot do the ×2, unfortunately, that YouTube provides. All right, so let's upgrade our dimensions to two-dimensional topological phases. And what I'm writing here is a typical Hamiltonian for the Bernoulli-Hughes-Chang type anomalous quantum Hall phase. And look at the spin-orbit coupled Hamiltonian. Momentum in the x direction would be multiplied by sigma x, the spin in the x direction, momentum in y, sigma y. And now let's take, so we're thinking about 2 dimensions, so momentum is 2-dimensional objects. The spin is still 3-dimensional. Let's have 1 minus p squared in the z direction. If you plot the dispersion of this baby, it looks like just an innocent valence conduction band from semiconductor. But now you can start asking, what's the spin direction in each momentum state, and whether it wraps around the Bloch sphere or not as a function of this 2-dimensional momentum. So if you look at 0 momentum, a little bit away from 0 momentum, this thing is mostly 1, so the spin wants to point in the z direction. Px and py start gaining steam and tilting the spin in the direction a little bit away from the North Pole into the northern hemisphere. Now, if we explore higher and higher momentum, we'll see that more and more of the Bloch sphere can get covered because of the px and py starting to get dominant. And because at some point the momentum will overcome this one, the spin will even reach the southern hemisphere and all the way to the South Pole, giving you a full wrapping of the Bloch sphere. That's an indication of a 2-dimensional topological phase, 2-dimensional anomalous quantum Hall. In fact, this wrapping is directly proportional. This is a Chen insulator. It's directly proportional. Let me just say this, I don't have a slide to correspond to it. It's directly proportional to the Hall conductance of this band. If you have a full wrapping, you have a Hall conductance that's quantized at squared over h. Okay. Now, I was cheating because I was doing momentum as a continuous variable going from 0 to infinity. It's not. It should be more like from minus pi to pi in each direction, like I showed you before, thinking about a square lattice with some specific hoppings, complex hoppings between nearest neighbors. No problem. Every time you see a px, change it to sine px. Every time you see a py, change it to sine py. And likewise, when you see a p squared, change it to 1 minus cosine. And that would be the type of Hamiltonian that results. And you can ask the same question about wrapping of the Bloch sphere by asking what the spin does in the Brillouin zone from minus pi to pi in the x and y direction. For my purposes, I don't want to think about sigma xy. I don't want to think about bands. I don't want to be confused between h and h bar with the entire band. I want to think about the motion of a single electron in such a band. So what's the motion of an electron in an anomalous Hall band, in a Chern band? We can go back to our physics 1 or high school days and recall that motion with the magnetic field has force equals the charge times velocity cross magnetic field. An electron has a negative charge, so it's magnetic field cross velocity. The usual magnetic Lorentz force. But what happens when you have Berry curvature? You have essentially the same equation. However, momentum and velocity, momentum and location are exchanged. So in addition, this force due to the magnetic field, you have a velocity that's determined by the group velocity, the derivative of the energy with respect to momentum, plus a Berry curvature. There's like a magnetic field. It crosses the velocity in momentum space. It crosses the momentum derivative to give you an anomalous velocity perpendicular to any force. What is the Berry curvature? It is derived from the Berry connection. So instead of a vector potential, we think of a Berry connection given by this expression, derivative of the wave function as a function of momentum. And the Berry curvature is like a magnetic field. It's the curl in momentum space of that Berry connection. In 2 dimensions, think about it like a magnetic field pointing out of the plane. Now, I didn't do a simulation of that, but I did a PowerPoint animation for this. So take the anomalous quantum Hall band that I showed you before, inspired by the Benedict-Hughes-Chang Hamiltonian. Here's a color map for the Berry curvature, the function of momentum. And let's think of a particle that starts off somewhere in the Brillouin zone, and we are applying a force in the x dimension on it, in the x direction on it. Let me describe what's going to happen so you can look out for it. You know, the force is going to try to move the electron, move the particle in the x direction, but this is a finite band. So there's going to be Bloch oscillations that are going to make the particle go one direction, but then as you go to the negative momentum, group velocity is going to change sign, the particle is going to go back to where it started. No actual net motion in the x direction on average. Why? Because you can't give the electron enough kinetic energy, right? The force cannot do work on the electron unless the electron goes to higher bands, which we're not allowing here. However, in the y direction, this term is going to play a role. And z cross x will give you y direction motion that can actually accumulate. That's the origin of this quantum Hall, this anomalous Hall response of Chern bands. So let me show my animation. You see as the particle goes through this high Berry curvature location, it moves up in the y direction. Whereas in the x direction, it goes back pretty much to where it started. So I need to have this animation in mind because we'll use it later on in the talk on a couple of occasions. I think that concludes my introduction to topological phases. So any questions at this point?
So if you do have questions, it's perhaps a good way to go about it to put it in the chat. Then I see it immediately. Otherwise, I have to scroll through 87.
Yeah. Actually, I would suggest if you have questions, unmute yourselves and scream at me.
That's also.
just say, yeah, I have a question, and go ahead. So anybody brave enough to unmute and ask a question? If you want to keep yourself on mute, generally that's fine. The background noise is good. A lot of echo in my office. Right, so if no questions, then let me...
There is one now. Vijay, do you want to voice it aloud? Oh, Vijay.
Yes, I have no idea about Berry curvature. And if you could give a sentence or two about it, it would be nice. Thank you.
Absolutely. So let me explain again. So Berry connection is a statement about how a wave function evolves as you change it to some process. But you can think about it as how a wave function evolves as a particle changes its momentum. If you don't have a spin, nothing happens. Wave function goes from e to the ipx to e to the ip plus dpx. However, if you have a spin, for instance, you can imagine that the spin actually twists a little bit as momentum changes. And then you can ask about the overlap of a state with momentum slightly different than the original state, and the spin is going to be slightly shifted. That's going to give an overlap that's 1 minus some imaginary part. That imaginary part is like an extra phase on the wave function that's going to change its wave packet dynamics. And it's quantified by this object, gradient with respect to some parameter, in this case momentum, of the wave function. This is a real field that draws its vector components from the gradient. And the thing that it produces, if you have a beam of particles, right, in slightly different momentum, there's going to be an accumulated phase in that wave packet, a different momentum. That accumulated phase is going to give you the impression of a momentum perpendicular to the motion, kind of like going through a magnetic flux. And that's quantified by this Berry curvature. That effect of an extra phase that's accumulated because of a momentum spread, then sending wave packets sideways, that's quantized by this Berry curvature. It's again a gradient of this gradient in momentum, but it has, but you care about this gradient perpendicular to the actual vector potential, and it gives you an anomalous motion. Namely, if you have this Berry curvature, if you're now pulling on a particle in the x direction, so I guess to the right in my screen, you're going to have not a force, but a speed that's produced in the perpendicular direction. And this is an analogy to a particle moving in the x direction in a magnetic field and feeling a force in the y direction. If the particle is massless, these two things are the same, I think. You just have motion perpendicular to the field. So the force and the motion are perpendicular to each other, and the proportionality is either the magnetic field or the Berry curvature.
Thanks.
If the particle is massive, then something else is happening. Is this satisfactory? Cool. Now the thing is, the Berry curvature integrates to an integer, or to I think some integer multiple of 2 pi squared in this case. But I won't bet my life on what I just said. But it's quantized as you integrate it over the band. Other questions?
Thanks.
Great. So I was wrong. I have one more slide of introduction. But yeah, another question, Dimitri?
Yeah, thanks. So I had a question about how you identify the physical quantities that correspond to the topological quantities. So the example that's in my mind is when you calculate the Hall conductivity for a Landau level system using the Kubo formula, it sort of seems like a conspiracy that outpops the Berry curvature as the thing that determines the conductivity. So is there a way, given knowledge of the topological invariants, that you can identify the physical quantities they correspond to?
Yeah, that's a great question. And in this case, it's really, God is in the details, in my opinion. You write the Kubo formula, and so I wouldn't say that the Kubo formula is always derived from topology. But it so happens that in 2 dimensions, the Kubo formula aligns completely with this invariant, with this topological invariant of how much of the Bloch sphere is covered. So there's and the way to see it is so in the Kubo formula you have a denominator of energy differences, right?
Yeah.
And you also have current correlators. So you have the momentum derivative to get the currents, right? So then, the momentum derivative of the Hamiltonian is the velocity. The momentum derivative of the wave function, gives you the Berry connection. And then somehow it conspires to give you the Pontryagin construction that I showed you before of the spin direction. But it's only true in 2 dimensions. Now, in different dimensionalities, it would be different quantities that reduce to the topological element. For instance, in one dimension, you can get a Thales pump, and then as you change momentum from minus pi to pi, so as you can change the phase of a band gap term, the phase of backscatter in your Hamiltonian in one dimension, from minus pi to pi, from 0 to 2 pi. And then you can ask how many particles move from side to side in the wire. So to do that, you'll have to integrate from momentum from minus pi to pi. And there you go. Again, you have a two-dimensional integral. Instead of momentum x, momentum y, you have momentum and some parameter in your Hamiltonian. And again, because velocity or current are associated with momentum derivative, you again reduce to a very curvature.
I see.
And you know, and in 3 dimensions, things are much more complicated. But it's a different quantity at each time that corresponds to this topological objects. But in 2 dimensions, it's just so intuitive. You have a spin direction as a function of a 2-dimensional space, and you can just take the 2-dimensional space, think about it as paper, and wrap it on a sphere.
Yeah.
Right?
Yeah.
And it so happens that that's the conductivity. I don't have anything deeper to say about this, but maybe some people in the audience want to say something deeper.
Thanks very much.
Sure. Other questions? All right, so one more slide of introduction, I guess, is what I was describing actually happens in nature, as we know. So 15 years ago, I guess Bernavik, Hughes, and Jang came up with this model, and it was realized by Lawrence Molenkamp's lab. And the statement was that if you have cadmium telluride, mercury telluride sandwich, then when the mercury telluride thickness goes above 6 nanometers, trivial semiconductors that you could think of using for an infrared detector becomes a rather interesting semiconductor with edge states going around the sample. From above, it would look something like this. So you have a 2-dimensional sheet representing this mercury telluride sandwich, and electrons would spin up, would start moving in one orientation around it, and spin down on the opposite orientation. So you have a metal that's bound to the edge of the semiconductor quantum well. What can you do with this? Oh, by the way, yes, I come from Los Angeles, so everything has to be represented in terms of highways for me. So I found a satisfactory description online at some point of this idea of electrons that spin up going one way, electrons spin down going the other way. In an empty highway, so nothing interrupts them, they're protected, which is not like roads in Los Angeles, unfortunately. What can you do with this? Maybe you can make spintronic devices. Maybe you can make dissipationless leads whose dissipation is independent of the length of the conductor. Majorana fermions, we covered already. Not going to talk about it again. Maybe you can make these things into quantum computing devices. That is all good and well, but away from my talk. I wanted to think about how you can apply these topological ideas into systems that are driven by light. Can we induce topological behavior by illuminating a semiconductor, a trivial semiconductor? Can we make special topological photonic states? Maybe we can use this for new paradigms for infrared detection. I'm raising this, but I'll actually skip it in my talk. And finally, the topological behavior might give us new paradigms for purely photonic control in zero-dimensional systems. Thinking about new ways of amplifying light. But whatever I'll talk about, my perspective is that everything looks better when you turn on the light on it. Right, so let's see. So the first thing I want to show you is how you can take a semiconductor. So this is how I started at it. You take a semiconductor that's trivial, doesn't have enough spin-orbit coupling in order to produce an anomalous Chern band. And by illuminating it with well-appointed light, you can make it into a topological phase. So let's see how that would work. Let's start with a non-topological 2-dimensional band. Again, valence band, conduction band, a little bit of spin-orbit coupling, but not enough to produce a Bloch, a covering of the Bloch sphere, a wrapping of the Bloch sphere. We start with spin-up, go a little bit sideways, we look at higher momenta, but then at very large momenta, go back to the North Pole. No wrapping, no topology, no churn response, no churn insulator. That's a regular semiconductor with a little bit of spin-orbit coupling. Now, if we shine light on it, we can do the following trick. So here's how we do topology with light. If we shine light, we can create a resonance. Okay? We can create a ring of resonance in a particular momentum ring. We can do a rotating wave transformation that will bring these two bands together such that the light beam creates a degeneracy between here and here. It would look something like this. So if this is a cut through this two-dimensional dispersion, now we shine the light, we create resonances between these two black lines. And this is if we're bringing these two bands together. And then, as usual, we get avoided crossings in the places of resonance. In 1D, it looks similar to what we had before, with a little gap opening here and here. In this 2D dispersion, it starts looking like a volcano. This talk is covered with natural disasters. I'm sorry about that. It looks like a volcano with the bottom, with the center of the new valence band being actually the old bottom of the conduction band. And the edges of this volcano of a valence band, high momentum, just what the valence band used to be, away from the resonance. So we have a new band structure, and now we can ask about the spin configuration, this new band structure. Again, large momenta spin up just as it was in the original band structure, but then we transition into the spin down because the center of the valence band is the center of the old conduction band with the spin in the opposite direction. Check it out. We now have a wrapping from the North Pole to the South Pole of the Bloch sphere. And if we're lucky, if we did things right, we have a wrapping of the spin pointing in the XY direction at the new gap point, at the resonance ring. If we're lucky, we'll see the spin wrapping around the equator of the Bloch sphere, doing a vortex, as I showed you before, as a function of momentum along this resonance ring. Let's look a little bit under the hood to see how that would happen. So what we have essentially is a Hamiltonian that again looks like a spin orbit coupled Hamiltonian. But now, instead of using the spin, I'll use tau Pauli matrices to indicate valence and conduction band electrons. So tau down is valence band, tau up conduction band. Here's the original dispersion, epsilon p times tau z. But now we do a rotating, we create a hybridization between the valence and conduction band. What would it look like? A complex number, g, as a function of momentum, its real part multiplying tau x, its imaginary part multiplying tau y, creating these resonant transitions. And the rotating wave transformation is by taking away an omega over 2 on this epsilon p to create this degeneracy at the ring of resonance, where plus epsilon p minus epsilon p is omega. What is GQ? That's the question. Is just the matrix element between the valence and conduction band electrons with light. It's a complex number. And on the resonance ring, so check out the space, it's a little complicated. Momentum in X, momentum in Y. Yellow is the resonance ring, right? And the red arrow is in the complex plane for G. G may start real, turn a little imaginary, full imaginary on the ring, then wrap around the complex plane around the origin as we wrap around the valence, the resonance ring. That happens together with this, going from the North Pole to the South Pole of the Bloch band. We get a topological phase. So that's how we do a topological.
I had a quick question.
Yeah.
What's this light here? I mean, what does it exactly represent? What physical quantity is this?
I can shine. So what it represents is a light, electromagnetic field at the frequency omega that can create resonances, that can excite electrons from the valence band to the conduction band. Now, usually we think about it in terms of Fermi golden rule. So that's when the intensity is weak, and you just get absorption of individual photons, creating excitation of electrons. But if the amplitude is higher, you can get coherent Rabi oscillations between the valence band and conduction band. That's the regime that we are in.
Okay, fair. Right. Thank you.
But it's a question of how do you appoint the light? What light do you put in? So
could I just jump in quickly and ask you about the you're assuming that that everything is coherent here, and I'm wondering if are you going to talk later about what happens when you introduce decoherence, the decoherence timescales?
I'm not going to chat about this. I'm not going to talk about this. I'm going to show the ideal case. Of course, if you do have decoherence, okay, if your light field is not uniform in space, you can get topological defects with gapless states in them, something that Daniel Podolsky clarified. If the light is incoherent, you're going to heat up the system. I mean, there's no escape from that. You're going to create quenches that will end up with your electrons being equally up and down. You can deal with this heating processes. That's a different talk. You can engineer a bath that will stabilize the system onto a valence band. That's the Fouquet valence band for the electrons. But I'm going to not discuss this.
Okay, thanks.
But this is a question, what kind of light do we want to shine? So in this case, we get full wrapping in tau space, good enough for topology as in space. So here's an example of how that might work. Take a square lattice that gives you a semiconductor band structure. And this is really just a simple square lattice realization of the B-Z Hamiltonian in the non-topological phase. Now you can shine light that you can think about as magnetic field in the Z direction that oscillates in time. So think about just having the magnetic field perpendicular to the plane. And if you solve this exactly, what you find is a new band structure, as I was describing. So now, what this band structure is a function of momentum in the x direction, with all the y component momentum interlaid, so you see a whole band. This system is periodic in x, but not periodic in y, which means that it has edge states. And those edge states are seen here, appearing in the exact diagonalization, connecting the valence band, conduction band, just like the edge states that I was showing you in Mollenkamp's experiment. They appear in a topological two-dimensional band. So again, think about it as a cylinder. It's periodic in the x direction, but there's boundaries that stretch from minus L over 2 to minus L over 2 to L over 2. They are linearly dispersing one-dimensional bands. These are these lines. Think of Zeus as the entity that provides the light. In this case, must be happy, made topological phase. So that's the simplest example of using topology with light. Now, typically I have to answer questions about how to do this experimentally, and of course it's very tough. Maybe you want to use circularly polarized light, get the benefit of an electric field in the plane, moving the electrons. That's indeed better. I don't need to do it anymore because of some great experiments. So there was an experiment early on by New Gedik that took this idea and shined light on the surface of topological 3D insulator and showed that you get new Fouquet bands that he saw in ARPES with gaps appearing. It's hard to see the gaps, but I think if you look at it close enough, with enough hope, then you see new gaps opening in the dispersion of a Dirac cone irradiated by light. Those gaps are topological. They have edge states, one-dimensional edge states occurring if you were to probe that. So that was an early on demonstration of Fouquet bands in topological systems. But more recently, Draco Valerian's group showed this appearance of a sigma xy due to light looking at graphene. What they did is look at graphene, try to look at sigma xy by a reflection of a pulse over this waveguide, while irradiating the graphene with an intense infrared beam. What that infrared beam does, it creates new gaps, both at the Dirac cone and at finite frequency. When you probe transport in that irradiated graphene, what you find is a sigma xy signal that is there only when the light is on. And it's quantized. Or it could be traced back to quantized value. So that was a realization of this topological insulator in irradiated graphene. I have to say, we were thinking originally, so the work that I was describing to you was Victor Galitsky and Nathaniel Lindner, and we were thinking originally about quantum wells. The same physics occurs in graphene for creating gaps between finite momental states. There was a discussion of the gap that opens due to second order effects of the light at the center of the Dirac cone by Aoki and Oka. We showed that also creates topology. I think they came a little before us, so they get due respect for that. All right, so that's like ancient history of topological physics. Let's see, so I have about 50 minutes more or 10 minutes?
Nominally, yes. Of course, we had quite a bit of discussion following your encouragement. So I think it's fine if you go a little bit over time.
Okay, I'll try not to go too much over time, but do stop me still. The questions are great. So, apropos, any questions on this?
I suppose there is a question by Brian Core.
Mm-hmm. Go ahead, Brian.
Well, maybe we should discuss it later.
Okay, so we can have it in the end of the... but do continue asking questions. Okay, so one question that was already raised was what happens with decoherence, relaxation processes? Can we really get a phase that's topological by irradiating a bunch of electrons and creating a new valence band that's non-equilibrium? As I said, we thought about it. I got asked this many times in seminars years ago. And we had a whole different research program where we showed how you can engineer bands to stabilize Fouquet phase. That was done by Kartik Sitaram and Charles Bardeen and Nick Lindner and myself. That's a different talk. Maybe more appropriate to the seminar series, but we decided on this talk instead. So instead of being bothered, but I was bothered by this question of equilibration. Then I thought to myself, instead of taking a lot of light, making a lot of electrons form some kind of an edge state, can we have the same physics happening with just one photon? Namely, maybe you can shine one photon on the system, it will create an exciton, and maybe self-consistently that exciton will think that it's part of a topological Fouquet insulator and stay on the edge. So, and then propagate together photon exciton doing vacuum oscillations on the edge will constitute some kind of a signature of this Fouquet topological insulator. I wasn't sure it happens, but I was sure of one thing. So an exciton is a combination of an electron in the conduction band and a hole in the valence band. We know what a photon is. Not a bound state, but a superposition of these two is called a polariton. And I knew that if you make a topological polariton, you can call it a topolariton. And I thought this would be a great name, so therefore we have to do the research. In light of experience, it turns out the topolariton is not very easy to pronounce. It's not as bad as transition melody chalcogenides. But I think we did it before people had to practice transition melody chalcogenides, so this name of topolariton didn't catch on. But that's my only regret. So let's see how something like that would work. An exciton and photon, a polariton that is topological. Okay, so what are the ingredients for these topological polaritons? Excitons. What are excitons? We have a quantum well in 2D, an electron in the conduction band, and a hole in the valence band that have similar group velocities might form a bound state and move together. They have a momentum, difference in the momentum between the particle and the hole. And a dispersion that's roughly speaking the gap of the semiconductor plus a kinetic energy derived from the kinetic energy of the electron. That's an exciton. A photon, we also know what it is, but we want to concentrate the photons over a two-dimensional quantum well. Let's do it with two mirrors and create an optical cavity, a two-dimensional optical cavity. In this case, a photon would also have a dispersion, mostly a time momentum going like the speed of light, but with a small gap with small momenta because of the quantization in the z direction. And now I can take these two components and put them together, at least in a PowerPoint realization. Here's the cavity, there's a semiconductor inside. We have the photons, we have the excitons, they're both bosons, and they can hybridize. And at this absolute value of momentum, they form a resonance and an avoided crossing. This creates a lower polariton band and an upper polariton band. And they move together, the photon and the exciton move together, by which I mean they oscillate from one to the other. But at this point, I was too lazy to make this blinking in and out of the exciton and the photon as they do vacuum oscillations between each other. It was too complicated here for some reason. This is not a bound state of photon and exciton. This is an oscillation between an exciton and the photon gives us this polariton. Now, where can topology come in? You already know that I'm a big fan of spin-half descriptions. You can think of whether this particle is an exciton or a photon as a spin-half degree of freedom. A tau z, there is 1 for exciton and -1 for photon. And over here, it's like these two bands that mix. And they can have a Hamiltonian up to a tau-independent shift, which represents the kinetic energy. The Hamiltonian would have a spin-orbit coupling-like form, just like the Floquet-topological insulator. A momentum-dependent complex number G that tells you how the photon and the exciton mix, and the Z component that gives you the energy difference between them. And now, if this tau Z component is guaranteed to switch signs, because we know that if we go on the lower polariton band, we go from a photon to an exciton. Another question is, at this resonance ring, what happens to the XY components? What happens to this G? When it's spin orbit coupled materials, that G does exactly what we want. It does exactly what we had in the Floquet-topological insulator. It winds. And if it winds, as a function of momentum on the resonance ring, we get a topological polariton band. So again, these two components together gives you topology. Now, there's something else that needs to happen. You see, in this band structure, there's no gap. Right? In this energy, there's both lower polariton and upper polariton bands. If you want to induce a gap, you add a periodic potential to the exciton, and you also need a time reversal symmetry breaking. You need the magnetic field. So those are two additional ingredients. And then you get the polariton. Now, again, I can talk about realization in transition metal because gaussianides. I can talk about realizations in other systems, but I don't need to anymore. Because the the collaboration between Technion and Würzburg groups, Höfling and Segev and their groups, produce a realization of this in an array of indium arsenide dots. Well, what they showed, the array, the electric array, can give you a band structure like a photonic lattice that, in the absence of a magnetic field, looks like this, kind of like graphene dispersion. But when you turn a magnetic field, these gaps open up, and you get photonic states that appear in between that give you this topological polariton. So the indium oxide is a quantum well, semiconductor quantum well. The light produces excitons in it. And you can see that as a seed light over here, it propagates primarily on the edge. For the experts amongst you, this is a bosonic system. If you put the bosonic polariton over here, it's going to decay in momentum until it gets absorbed into the bulk band, which is empty, it's bosons. These are excited states of the light field. That decay into the band is what you see here. You know, light penetrating into the bulk of this material, but notwithstanding this edge. Any questions about polaritons and topological polaritons? I should acknowledge my collaborators. This was done with Torsten Kartzig, Charles Bardeen, and my partner in crime, Nick Lindner. Not the experiment, the theory. So questions on this?
Seems we don't have any questions at the moment.
Let me ask a quick question, and that is, why do you need the magnetic field? Why do you need time reversal breaking?
Oh, that's a great question. There's always things come in pairs here, right? So if you don't have the magnetic field and you try to create everything else, then you end up with polaritons wanting to propagate in both directions and on the same edge, and they'll scatter each other. There won't be any topology that emerges from this. Let me see if I can give a better answer. Yeah, I think that's it. You really want this. You want the circulation of the exciton photon matrix element to be of a particular sense as you wrap around the resonance ring. But in all real materials, you get two resonance rings between excitons and light. And the topology of them usually cancels each other because the time reversal invariant, the time reversal partners. The magnetic field breaks that and creates differences between these two band crossings or band gaps. So no matter what system you're looking at, if it doesn't have time reversal broken, you can't have states propagating in one direction. And if you don't have states propagating in one direction, they can scatter into each other, they can hybridize, you won't have a topological system. In this case, we need the time reversal symmetry.
Thanks.
Sure. Right, so the last thing I wanted to touch is how these ideas play in synthetic dimensions. And it's not complicated. I think once you've survived everything else intact, you can get this very quickly. Sorry, I can take a few minutes to do that. Alex, is that permitted? Right, so
That's good.
So the idea is that, you know, we were talking about periodic drive, hybridization of light and matter. Now what I want to say is that periodic drive can be thought of as an extra dimension. I wanted to describe this with some animation or some graphics. I couldn't come up with anything, so I searched the web far and wide. And the closest thing that I got to is this graphics from a TV show of my childhood, Time Tunnel, where this time tunnel was a periodic structure in space that made you believe that these people can travel in time. Now I have the opposite. A periodic structure in time should make you believe like you can travel in space. That's how close I got to it. It's a really great show. I can recommend it if you're sick of like contemporary shows. It's a Cold War era, black and white, etc. But I think I'm missing out on the generation. How many have seen this time tunnel show? None. Never mind. Might be a fluke of Israeli TV in the 80s. All right. So synthetic dimensions give new control paradigms for light. That's the goal in the next few minutes to show you this. All right, so forget about old TV shows. Let's talk business. So if we have a simple drive of a Hamiltonian, we have say a 2x2 Hamiltonian, it's driven by some periodic field. I want to talk about the limit of a slow drive frequency that's much smaller than the Hamiltonian magnitude, than the strength of the Hamiltonian. In which case, we don't want to talk about Fouquet wave functions. We want to talk about expanding the evolution of the wave function in the harmonics of the drive. You can always write this. We can always write the time dependence of the wave function broken down into harmonics times time-dependent wave functions for each harmonic. You take this ansatz, you stick it into time-dependent Schrödinger equation, and separate by harmonics, and what you get is just a tight-binding Hamiltonian, H0 on the side, psi n, and V serving as hopping to n+1 and n-1. This is a synthetic dimension. The number of photons you took from the drive is like a lattice. You have to pay a price. Photons come with an energy. Each site has a different energy because of the energy you took from the photon field. So in fact, this describes a one-dimensional system that's sloped. If the slope is not high, then it really is like an extended one-dimensional system. And this has been explored by many others like Nathan Goldman, Charlie Fan, Jacopo Carlosotto, Muhammad Hafezi, and Gil Refael, and others. So this is a one-dimensional system that we get just because of the drive. Can we do this in 2 dimensions? Why not? Let's have 2 drives, V1 and V2, omega 1, omega 2, and expand the wave function in harmonics of these 2 drives. This describes a 2-dimensional lattice. And now the energy cost of taking photons from the drive is like a frequency, is like a force field that's tilted with components omega 1 and omega 2. Now, so we have a tilted 2-dimensional lattice, which means that motion by energy conservation is going to be restricted to a strip that's perpendicular to this effective force in the synthetic dimension. How come? This is the strip in which this thing is constant. The motion is free on it. Okay, so these are the constraints of this 2-dimensional synthetic construction. Clear so far? What do I want to do with this? I wanted to show you how, using this idea, I can make a 2-dimensional topological phase in a 0-dimensional system. Just one spin. Here goes. This was done with Ivar Martin and Bert Hopper not so long ago. We can use the BHZ band structure, sine px, sine py, sigma x, sigma y, spin orbit coupling, as we love. And now I'm going to do the following trick. So this is a Chern band, describing a Chern band. It's topological when m is smaller than 2b. Now I'm going to do the following transition. Instead of px, I write omega 1t. Instead of py, I write omega 2t. And now what we have is just a spin that's driven by 2 circularly polarized, elliptically polarized light beams. Why elliptically polarized? Omega 1 gives you sigma x and sigma z component. The omega 2 gives you a sigma y and sigma z component. But this is topological phase. What's the consequence? Just as you have perpendicular motion in the xy plane of electrons in the Chern band, over here you're going to have perpendicular motion in the synthetic dimension, which means amplification of one of the beams at the expense of the other beam. So let me explain quickly how that happens. So let's go back to my favorite slide, simulating the Berry curvature. So now instead of having px and py, we really have the phases of one drive and second drive. But my time-dependent Hamiltonian describes an electron that is, it seems as if it's being driven by a force along the valence band of a 2-dimensional quantum well. It's no different. It's just the momentum is dictated by force times time. What is the force? Omega 1 and omega 2. We have a Berry curvature map for the drive scheme. It's a function of P1 and P2. And now my spin is going to go through the Brillouin zone, but in a very appointed path, like so. Every time that it hits high Berry curvature, it's going to climb up this energy conserving strip, converting omega 1 photons into omega 2 photons. I'll show you this again. every time that the spin goes through high Berry curvature regions, it climbs up. Now, and you see this line is just using the periodic properties of the Photon zone going from here to here, and then here, etc. If omega 1 and omega 2 are incommensurate, we just cover the entire Photon zone. We average over it, we get the average Berry curvature, which is the Chern number over 2 pi. Now the equations of motion of this velocity in the n space, dn dt, is the Berry curvature across the force. The force is omega 1, omega 2, which means if we want to know how much work drive 1 does, it's like dE1 dt is omega 1 times dN1 dt. Same for 2. But dN1 dt, you can read from here. It will be the Berry curvature across the force, Berry curvature times the frequency of the other drive, the perpendicular directions. This will give us a topological frequency conversion with the quantized value of the Chern number over 2 pi. So this motion in this energy conserving strip is dictated by topology to be at this rate. Chern number over 2 pi, omega 1, omega 2. But that's a frequency conversion that doesn't care about the frequencies. It doesn't conserve the number of photons. So it does not require resonance. And it might actually work for a terahertz regime when we have very few ways of controlling photons. Questions on this idea? So this is the topological phase, zero-dimensional system just because of the drug.
So what's the entity that's topologically protected, if that question makes sense?
That question makes sense, and it was asked to me by Pete Brower on several occasions. And the answer is, here it's disorder in the drive. So if the two drives have a phase that oscillates in time, as you know, lasers have a finite coherence time, it turns out that this pumping will be topological. This pumping would be even better quantized under these conditions. In particular, if your omega 1 and omega 2 are harmonics of each other, they're not incommensurate. They have some rational fraction as the ratio between them. You don't get quantization. You just get some kind of you can get pumping of arbitrary value depending on the Berry curvature that you visit. But,
I have a naive question.
let me just finish the thought. And then if you have a random phase fluctuation, then you just average over the entire Photon zone to get this topological number. That's topological protection. So Abhijit, sorry, I interrupted.
Yeah, I mean, I was just curious as to what happens if you hook this up to a bat. Just curious what would end up happening. Does this still remain?
It's a great, actually a bath is a good thing. So Frederick Nason joined us in this collaboration and simulated this with a bath. What a bath does is makes sure that the spin is pointing in the direction of the instantaneous magnetic field, the instantaneous ion field. You see in this diagram that I have this spin like an electron in the valence band. This is a non-equilibrium situation. If you drive too hard, that spin will go up to the opposite band, and that motion, instead of being quantized in this direction, it will be in the opposite direction.
Right.
Actually make sure that the spin always relaxes to the lower energy state. It's a good thing.
Right. So the dissipation ensures that you remain in the low energy surface. Is that what he's saying?
Yeah, because every time that you go to the high energy, you dissipate into the bath. You go back to the low energy, and then your system can continue.
But the effective conclusion about the topological pumping remains more or less the same.
Yeah, and we simulated that.
Right.
Apply it in various circumstances. For instance, instead of one of the drives, you can have a cavity. Fill up the cavity this way. So if you have a laser and a cavity that are not in the same frequency range,
Right.
you can use this. You can put the spin half inside the cavity, drive the spin half, or cloud of spin halves, drive those spin halves, and fill up the cavity despite the lack of resonance.
That's interesting. Thanks.
Those are papers with Frederick Nathan. Sure.
Yeah.
Let me come close to the conclusion, then open the floor to more questions. Yeah.
Okay.
Go ahead,
Okay,
Nancy.
I have hi. Yeah, as you must have seen, we're with the same link with Sergio. But okay, finish and I will ask the question.
Okay, so I want to say this is not just theoretical. We hope that you can actually realize this. So what I showed you is that you can take a spin half, double pump it to get an amplification. Can we do it for an electronic system? Maybe valence semimetal would be good, because valence semimetal has a Hamiltonian that already looks like sigma dot momentum, sigma dot the vector potential. Then you can drive the vector potential to give you this. You have the many electrons give you this effect. So this is what Frederick, Ivar, and I have been working over the last years, and now we're finally getting ready to publish. And the answer is yes. You can take valence semimetal, which has a Dirac cone dispersion, shine two beams of light on it, and see how one light is depleted and the other light is amplified. The ideal conversion in the valence semimetal could be enormous for a modest field of 1 megavolt per meter, very modest laser field. You'll get an optimal conversion that could be 10 to the 12th watt per cubic centimeter of material in the terahertz regime. It's enormous. It cannot be true. Of course, recombination in the valence semimetal gives you what we call a ring of fire dissipation, which also goes like E cubed. And so if E cubed over omega for the optimal power conversion, you get a heating that's E cubed over omega tau. If you want this to be practical, you need the relaxation time in the valence semimetal to be much longer than the period of the drive. And indeed, under a regime of relaxation time in the tens and hundreds of picoseconds, we can see positive conversion rates in valence semimetal in simulations. This is for incommensurate frequencies. Straight off the simulation board, we know that now this whole line goes up quite a bit if we use frequencies that are rational fractions of each other. So I don't have a graph to show it, but it seems that starting with a few tens of picoseconds of relaxation time, we get positive conversion power for the system. So this is still work in progress. That's what we're doing right now. And you can ask me about this if you're interested, but otherwise let me just, that's what I was saying, harmonic frequency combination should do even better. Let me do a quick advertisement. Christina Saradaki was a postdoc with us over the last year, and she's moving to Cologne to finish her Marie Curie fellowship. She was investigating just energy pumping in random doubly-driven Hamiltonians and showed that generically shows interesting features and the transition, depending on the strength of the drives, between triangular-like distributions of energy pumping and Lorentzian-like. She was thinking about it as like any random matrix, doubly driven, has this feature of energy pumping. And it's worthwhile investigating the statistical properties of this, because this could be a basic of quantum machines for photonic control. So, just the conclusions: new control paradigms for topological phases, new topological bosons, the polaritons. We can get topological frequency conversion in applications of infrared detection, as well as amplification of terahertz light in some of these new topological materials like valence semimetals. These are, I touched upon 3 of these 4 things. If you're curious about this, I can tell you about this. But sorry for taking so much extra time. So thank you for your attention so far. And let me open for questions for whoever has the energy still.
Yeah, let's thank Gil for a very stimulating and also very pedagogical talk. Thank you so much. There've already been great questions. Are there some other questions?
Yeah, I have one that I think you partially answered with your last Weil semi-metal example. While you were talking about the optical amplifiers, I had in mind a spin and how the spin was winding as it was pumped by these two lasers. And I was wondering, from a practical point of view, we know that the spin light coupling is very, very weak. So I was wondering how much you could see these type of effects. But somehow, yeah, you address it with the Weil. So can you expand a little bit on that?
Absolutely. This is something that was top on our minds. So this was in the weak, this is in the strong driving limit, where the amplitude of the drive has to be bigger than the frequency. That limits us to terahertz frequencies and lower. So first of all, there was this effect was demonstrated on the spin on the IBM quantum computer. It's not exactly an application that you want to think about too hard, but that was interesting. And then you can realize it with radio frequency easily. So you can do it easily with radio. And so you can pump energy in a quantum computer. You can do it with radio frequencies. The applications not very close to applications. But terahertz is where it starts being viable. And Weil semi-metal doesn't have a gap.
Yeah.
You can actually explore doing things to electrons that are closer to the whose Hamiltonian is weak relative to terahertz. And I didn't explain this, but I'm happy to expand now. So this is a map of momentum space of a Weil semi-metal, a cut of it. And what you see is regions that convert power in one direction, red, in the opposite direction, blue. As it always happens, electrons are like ants. They don't want to push in the same direction. They push in some random direction and hope that they average into something. And this is the case here. So if you have a type 2 Weil semi-metal, or at least a strong velocity anisotropy, you get a Fermi surface that looks more like this. And then you get only the small momentum electron states to contribute to the pumping. So and then this ring of fire is when the frequency of the light starts being resonant with transitions across the backbone.
Between the two cones.
Right. And this, and you know, so you see circles here. Those circles are really the trajectories that momentum states take because of vector potential that we add to them. So this is, you know,
okay.
I'm happy to explain more in private, or you know, there should be in a couple of weeks the paper describing all this work, non-equilibrium and Weil. But the upshot is small energy gaps. So yeah, I'm saying something that's a little funny. So
no,
this is where the frequency is. We want energy. We want the gap of the electrons to be bigger than the terahertz, right?
Yeah.
And comparable. And then
yeah, you're talking 10 millielectron volts, 15 millielectron volts, that order of gaps.
Lower, even lower.
Right, lower. Yeah.
Yeah. I think let me try to say this again. So you look at this map. You see a Fermi surface, right? You see trajectories that the electrons take. These trajectories are the ones where the electrons are resonant, or they go through resonance, right? This is you know, this area is the terahertz gap. We want momentum states with bigger than terahertz gap, because we want the Hamiltonian to be stronger than but we want the trajectories to go around the Weil point. This is the Weil point. We want the trajectories to go around the Weil point to get topology.
Yes.
If the energy is too big, then the trajectories that the electron does in momentum space doesn't include the Weil point, does not have a wrapping.
Okay.
It really maps back to this topological insulator.
Yeah.
If the momentum is too small, the Hamiltonian is smaller than the frequency.
Mhm.
That gives you the range of active electrons in the compound.
So,
And those are the red and blue that you see.
okay. So it's a very, very well-tuned regime.
Yeah, and you know,
Yeah.
I don't know that you can realize it in nature. That's what we're trying to push. And if you cannot realize absolute pumping, you realize the following effect. You try to penetrate a vial slab with this two pieces of light, they'll get absorbed. But one of them will have an absorption that's longer. So it will decay over longer depending on the amplitude of the other drug. So how fast things are absorbed will be controlled. That's an experiment that one can do right now. If you want to make it into a substitute for optical parametric amplifiers, you need to optimize the material and the drive stream. This is kind of first shot.
Okay. As always, very nice talk, Gil. Yes.
Thank you all for attending. Yeah, other questions?
Any other questions for Gil?
Yeah, could I ask a quick naive question?
Absolutely.
So you mentioned earlier that we can use this paradigm of light affecting the topological states to induce topological states. Is there a long-term hope to use that for quantum gates or another aspect of quantum control?
It's a good question. I think when you want to do quantum gates and quantum control, you want to be what do I say? From my experience, it seems that topological tricks for quantum control of qubits are not super useful because the topology comes in as something that can stabilize long range, maybe long time phases. And you know, but you might use some of those tricks for specific things. But the toolbox of quantum control is actually really big. It took me a while to appreciate this. And it has to do with a lot of brute force manipulations. You know, maybe some of the brute force manipulations could be interpreted topologically.
Okay.
But you know, so far I didn't find that a big application of topological control into this. One exception, we showed in a paper with Bella Bauer meeting with Tommy Perrig-Barnett and Thorsten Kartzed and Yuval Oreg that you can induce in Yang you can induce extra Majorana modes by a drive. You can induce non-equilibrium Majorana modes in one of those one-dimensional driven systems or two-dimensional driven systems. Those Majorana modes may appear at omega over 2. They're actually the thing that's at the basis of time crystals.
Okay.
Non-equilibrium Majorana modes, and you can braid those non-equilibrium Majorana modes as well. And you can create braiding schemes that you would naively think you cannot make in a one-dimensional system. Let me say this again. So when you want braiding of Majoranas to carry out gates, you think about two-dimensional systems where you can really take Majoranas around each other and take advantage of their of the non-abelian statistics, right? In one dimension, you shouldn't be able to do this because the Majoranas will collide and not braid them. But if you add the synthetic dimension of time, then you can actually make sequences where you create two Majoranas, say at 0 frequency, then you convert them into omega over 2 Majoranas, bring them back, or do a sequence that's like wrapping around this rectangle. That will give you the braiding. In the rectangle, let me say this again. You create two Majoranas at 0 frequencies, you take one of them and make it into a non-equilibrium Majorana and bring it back. There you go, you braided them. That's one application of this that's possible.
I got it. Thank you.
Sure.
So in view of time, I would say let's thank Gil once more for a very interesting talk and also for a great discussion. I'm really looking forward to your preprints. So let me quickly say next week we are having Peter Reimann talk about foundations of statistical mechanics in and out of equilibrium. I hope to see you all back next week, same time. And thanks so much again, Gil.
Thank you all. Thank you for attending and sorry for taking so much extra time.
No, that was great. I think we all enjoyed it.
Thanks, good to see you all. So log out.
Yeah.
Thank you.
Bye-bye.
Bye-bye.